Like, what are the topics that have been covered? Hello? Yeah, you can respond, like,
சார் தமிழ்ல சொல்லுங்க சார்.
oh, sorry, Tamil, I don't know Tamil. English, it's okay.
ஓகே சார்.
Okay. So, what have been taught in class till now? Like, thermodynamics, you have been taught? Entropy. Hello?
Yes, sir.
What topics have been covered in class till now? So, yes, hello. So, is it okay if I discuss like problems on entropy today? Yes. Hello. Hello.
சார்
Yes. So, is it okay if I discuss some problems on entropy and thermodynamics today? Assignment questions, previous year's assignments. Yes or no? I mean, you can say yes or no, like if I ask something, right?
Sir, I cannot understand English, sir. Tamil speak now, sir.
Okay. If I actually, I don't know Tamil. I'm not from Tamil Nadu. Okay. So it is difficult for me. But if I write something in the chat in English, will that be okay? If I write something in the chat, will you be able to understand? Okay, wait a minute. Can you see my screen over here?
Yes, sir.
எஸ் சார்.
Okay. Okay, so let's start. Um, First question. The entropy of an isolated system always dash and becomes a dash at the stable equilibrium. So what will be the answer in this case? What is there in the first dash and the second dash? Uh, Entropy of an isolated system always increases, right?
இன்க்ரீஸ் மேக்ஸிமம் சார்.
Right. So for an isolated system, entropy will always increase. And when it reaches equilibrium, it will be maximum. So the correct option is option 2. Okay. Next question. Which of these following statements is true? So can you tell me which of these statements, these 4 statements is true? So let me say, is this last statement correct statement? Different microstates correspond to different macrostates always.
Entropy is function of the microscope of the system, sir.
Uh, no, actually, entropy is not a function of the microstates. Why? Because entropy is a macroscopic property of a system, right? So, for example, if I have, say, 5 red cards and 3 black cards, you know cards, right? So I have total number of 8 cards. Okay, 5 red and 3 black. Now I can choose 5 red cards in many different ways, and 3 cards in many different ways. Okay, so each of these corresponds to a given microstate, each of my choices. Okay, so each of these arrangement is a microstate, and the entropy is what comes out of those microstates. So it is a property of the macroscopic property of the system. Okay, so it is not a function of the microstates because my set of cards will always have the same entropy. Okay, so the correct option here is option A, the first one, that a given macrostate typically corresponds to a large number of microstates. Is this okay? Clear, no?
Okay, sir.
Okay. Now coming to this question, that if I have a deck of cards and I have a hand of 8 cards, so I have 8 cards in my hand. Out of my 8 cards, there are 5 cards which are black and the other 3 cards are red in color. Okay, so you have seen cards, right? Cards have 2 colors, black and red. So out of 8 cards, 5 are black and 3 are red. So now I have to calculate the entropy of this system. Okay, so how do I do that? So n here, n is the total number of cards, n equal to 8, right? Number of black cards is 5, number of red cards is 3. Okay, now total number of cards is 52. Out of 52 cards, 26 cards are red and 26 cards are black, right? So
Yes, sir.
out of 26 red colored cards, I can choose 3 cards in how many ways? 26C3. So you are familiar with this notation, right? 26C3. This thing you have come across, right? In mathematics or other courses. Right. Similarly, out of 26 black cards, you can choose 5 black cards in 26 C5 ways. Right? Yes.
சார் ஃபர்ஸ்ட் ஒன்னு என்ன சார் இருக்கு?
Answer. Answer is not first one. Answer is last one. So how I come to that answer is like this. So these are the number of ways in which I can choose my red cards. And these are the number of ways in which I can choose my black cards. Okay. So the total number of microstates which I have is a product of these two. So basically the total number of ways in which I can choose 5 red cards and 3 black cards. Right? So that is why the entropy of the system, it is log of this total number of microstates. right? So if I calculate this logarithm, then my answer turns out to be this. Okay. You understood how to do this, right? Uh, okay. Is this clear? Okay. So if you have any question, just ask. Okay. So this next question is that Alice has 3 black cards and 3 red cards in a hand picked from a deck of 52 cards, while Bob has 4 black cards and 2 red cards from the same deck. So whose cards have a higher value of entropy? So here also we will proceed in the same way. That is, first for Alice, she has 3 red cards NR and 3 black cards NB. So total number of cards is NR plus NB, which is equal to 6. So then the number of ways in which she can pick up 3 red cards and 3 black cards from that entire deck is basically given by NA, which is 26C3 for red cards multiplied by 26C3 for black cards. So accordingly, the entropy will be logarithm of NA, which is this. Okay. And for Bob also similar thing we have to do. So number of red cards is 2 and number of black cards is 4. So the number of ways he can choose 2 red cards and 4 black cards is basically NB, which is 26C4 into 26C2. So then in his case, the entropy becomes logarithm of this quantity. So if you calculate these two logarithms, you will find that the entropy for Alice is greater than entropy for Bob. Okay. Is this clear to you? Yes.
Yes, sir.
Okay. Now going to question number 5. Now we have to consider a case where there are 3 steps. So suppose you're standing in a staircase which has only 3 steps. Each step has the same height, which is equal to h. And there are 3 different people on the staircase having equal weight. So I can say that there are 3 different people, A, B, and C. Each of A, B, and C have the same weight, and they're standing on the 3 steps of the staircase. Each step has a height of h. So in how many ways can the potential energy be equal to 8 Wh? So you know that potential energy is basically mass into gravity into height, right? Basically weight into height. So you have to find out how many ways in which potential energy can be 8 Wh. So here is the diagram. So these are the 3 steps. One has height h, this one has height 2h, and this one has height 3h. Okay. So the number of ways in which potential energy can be equal to 8h, 8 Wh is basically the number of ways I can write 8 as a sum of 3 integers. Why? Because there are 3 people, each has a weight of W. So if I can write 8W in terms of a sum of 3 multiples of W, then those are the number of ways I can have this value of potential energy. Right. So there is only one way I can have a potential energy of 8 Wh, and that is if I have 2 people standing on the top step and one person standing in the middle step. Okay, this part is clear, right? Hello?
Sir,
Yeah?
nothing, sir.
Okay. So the only combination is that I can have two people standing on this step and one person standing on this step. Now I can have person A over here and B and C over here. I can also have B here, A and C over here, and then I can have C here and A and B over here. So you can see that there are three ways in which I can form an arrangement like this, which has a potential energy of 8 Wh. So the number of ways the potential energy can be equal to this is equal to 3. Okay. So then the next question, it asks that for this same system as above, the potential energy will have the which value of potential energy will have the maximum number of possible occurrences. So how many, so basically this asks me that if I have a potential energy of 3 Wh, then how many number of ways in which can I have this potential energy? Similarly, if I have a potential energy of 6 Wh, what are the possible ways in which I can get this value of the potential energy? Okay, so let's start from the beginning. Suppose my potential energy is 3 Wh. Since there are three people, it cannot be lower than this particular value. Okay, and a potential energy of 3 Wh with three people will mean that all of them will have to stand on the lower step. That is the only way in which U can be equal to 3 Wh. So that is why the number of microstates corresponding to this value of U is equal to 1. Okay. Now if my uh, potential energy is 4 Wh, then what happens is basically I have two people standing on this step and one person standing on this step. So 2 plus 1 is 4. That's why. And the number of possible ways in which I can have two people standing on this step and one on this step is equal to 3. So that is why for this n is equal to 3. Similarly, for 5 Wh, I will have two people standing here and one person standing here. And again, the number of possible arrangements is equal to 3 for this also. Now, when the energy is 6 Wh, then let us see how many ways we can have this arrangement. One is that I can have all three people standing on this step. So 2 plus 2 plus 2 equal to 6, right? The other possible arrangement in which I can have 6H is if I have 1 plus 2 plus 3. That is one person here, and one person here. And the number of ways in which I can form this particular arrangement is 3 factorial. Okay, basically I can reshuffle them in 6 different ways such that one person is standing on each step. So the number of microstates corresponding to this is 3 factorial plus 1, which is equal to 7. Okay, so this much is clear, right? Hello?
Sir,
Yes, clear question?
yes, sir.
Okay, clear, no? Okay, so similarly, if the value of U is equal to 7 Wh, then I will have two people standing here and one over here. So 2 plus 2 plus 3 is equal to 7. So again, number of possible arrangements is 3. For 8 Wh also, you will find that I should have two people on the top step and one person over here, like we saw before. So for this also is equal to 3. And for 9 Wh, it is equal to 1. So the value of U equal to 6 Wh can be possible in 7 different ways. So it has the maximum possible number of ways of occurrence, or this potential energy has the maximum number of microstates. Okay, so this is the potential energy which maximizes the entropy of the system, right? Now, in this example, you saw that the three people were different. So accordingly, I could arrange them in different ways. Now, what if instead of three different people, all three people are the same? Or let us say that I have three identical marbles instead of three different people. So now the thing is that you cannot differentiate between marbles. You cannot say that this marble is different from that marble because all of them are the same, right? So now you have the same staircase with three same marbles on them. And so then you have to find how many ways the potential energy can be equal to 6 Wh if all three marbles are the same. So what then happens is that 6 Wh, as I showed you, is possible if there are three marbles here, and if one marble is here, one marble is here, and one marble is here. So these are the possible ways in which you can have 6 Wh, right? Now, since I cannot say which marble is which, so I cannot simply interchange the marble from here to here and here to here and say that this is a different microstate. Why? Because this will be the same microstate as the earlier one, because the marbles are not differentiable from each other. Okay. So the number of ways in which I can get this energy state, if I have three identical marbles, is equal to 2. Okay. So is this clear? Uh, are there any questions? Okay. So if there are no questions, this is an important part in statistical mechanics, in the sense that you have to see whether the entities which you have are distinguishable or not. Basically, if you have distinguishable entities, you can have a different number of microstates than when you have non-distinguishable entities. So similarly, you will also see in the next classes for bosons and fermions. So bosons and fermions, as you know, fermions, I mean, many of them cannot sit together in one step. On the other hand, bosons, many of them can sit together in one step. So because of these constraints, these two systems will have also different entropies. Okay. So all these things will be covered in the next classes. So coming to this question number 8, for a system of marbles on an endless staircase, can there be a negative temperature? Okay. So can there be a negative temperature for a system of marbles on an endless staircase? Hello?
Sir,
Yes. Yes. Hello?
Sir,
Yeah. Any question?
true, sir.
Okay, true. You're saying there can be negative temperature for system of marbles on endless staircase. Why you're saying it is true? Why is it true? Actually, the correct answer here is that it is false. Why? Let me show you. Because you see, temperature is defined in this way. So, right. So, if I have entropy and versus the energy, then the temperature is defined as the derivative of this graph. Okay, or 1 by temperature is defined as the derivative of the graph of entropy versus energy, right? So, for example, here, over here, if I have a graph of entropy versus energy like this, so as you saw over here in this case, the entropy, it is very small when the energy are at the extreme values, and it is large at somewhere near the middle of the energy range, right? So the graph looks like an inverted parabola for entropy versus energy. Okay, it has a maximum value at some point in the middle and it falls off on either side, right? And 1 by temperature is the derivative of this graph of entropy versus energy. So if I take the derivative of this thing, then I will get 1 by temperature. Okay, now if I have a finite number of energy levels, or that is if I have a finite number of steps in my staircase, then my energy is always constrained between two values, a small value and a large value, maximum value and minimum value. Okay, so that is why in that case what happens is that there will always be a point where the graph of entropy will rise and then decrease. And in the decreasing part, I will get a negative temperature. But if the number of steps in the staircase is infinite, then this maximum value of energy will also be at infinity. All right. So what happens is that the entropy of the system will keep on increasing and there will be no maximum point. Okay. So that is why the temperature, that is the temperature, which is the derivative of this graph, can never be negative in that case. When my system size goes to infinity, then the temperature is always positive, right? So that is why for a system of marbles on an endless staircase, there cannot be cases of negative temperature. The temperature will always be positive. Okay. Okay, this is clear, right?
Sir,
Okay, that
eighth
is
question false.
eighth question. The answer is false. Yes, false.
Thank-
Okay. So you know about Carnot engine, right? Carnot engine you have seen. So pressure versus volume diagrams, you have done this in class, right? So what does a Carnot engine look like on a pressure volume diagram? So suppose my system is initially at point 1. Okay, then my system absorbs heat and its volume increases isothermally as the pressure decreases and it reaches point 2. Okay, and the amount of heat the system absorbs while going from 1 to 2 is Q hot. Once my system reaches state 2, the volume increases adiabatically and the pressure also falls and the temperature also goes down. So adiabatic means that there is no heat exchange during this process. Okay, that is how my system goes from 2 to 3. Now from 3 it goes to 4 by following another isothermal process. So as it goes from 3 to 4, the system again cools down, that is, the volume contracts, pressure increases, and from 4 to 1 it again goes via a adiabatic process. So here also there is no heat exchange between the system and the surroundings. So this is like a reversible process, and this reversible process is known as a Carnot cycle. Okay. So the question here is that in a Carnot cycle, if you have an ideal gas, then you have a particular temperature scale, which is theta, and the Carnot cycle has a thermodynamic temperature scale T. So, there are two types of temperature scales, theta and T. Okay. Now, if you perform on the ideal Carnot cycle on an ideal gas, you will see that these two temperature scales, theta and T, are the same. So this is what we have to prove. Now, the ideal gas satisfies this equation PV equal to N kb theta. Okay. And the internal energy of the ideal gas is E. And as you all know, for an ideal gas, internal energy is a function of temperature theta only. So first, we have to calculate the heat exchanges QH and QC as functions of theta H and theta C, and the volume expansion factors. So QH is basically the heat which is being absorbed in the system while it is going from 1 to 2. And QC is the heat which is given up by the system when it is going from 3 to 4. Okay. Theta C is the function along this isotherm, and theta H is the temperature along this isotherm. Okay. So since you already have this ideal gas equation PV equal to NkB theta, from this you can find theta as PV by NkB. Right. And for a Carnot cycle, you can define the temperature, thermodynamic temperature, in this formula for a reversible Carnot cycle. That is the temperature at the hot end divided by temperature at the cold part is equal to the heat absorbed by the hot part divided by the heat given up during the cold part. Okay. Now for an ideal gas, the internal energy is only a function of theta, as you know earlier. So you know the first law of thermodynamics, which states that the heat exchange is equal to the change in internal energy plus the work done on the system. Okay. So if I use the first law of thermodynamics here, then dE can be written as dE d theta into d theta, because E is only the function of theta, and dW is minus PdV. So dQ is equal to this quantity plus PdV. Okay. Now for the segment going from 1 to 2. 1 to 2 is an isotherm. Okay. And that means along an isotherm, d theta is equal to 0. All right. So since d theta is equal to 0, this quantity becomes 0, and my dq is equal to PdV. Okay. So for segment 1 to 2, dq is equal to PdV. So dq hot is PdV, therefore P is equal to, and where P is equal to Nk theta hot by V. This comes from the ideal gas equation. All right. So if I substitute this value of P over here, then dq is equal to Nkb theta hot by V dV. And if I integrate from V1 to V2, so V1 is the volume of the system at point 1, V2 is the volume of the system at point 2. If I integrate from V1 to V2, then I will get the total amount of heat which is absorbed as the system goes from 1 to 2. Okay, so Q hot is equal to Nkb theta hot ln V2 by V1. Similarly, if I do the same calculation for the process going from 3 to 4, then the amount of heat that is released by the system is Nkb theta cold ln V3 by V4, where theta cold is the temperature along this particular isotherm. Right. So then if I take the ratio of Q hot by Q cold, I get theta hot by theta cold ln V2 by V1 divided by ln V3 by V4. Okay. So this solves the first part. So here I have been able to show that the heat exchanges can be written as functions of the temperatures of the two isotherms. All right. Now I have to calculate the volume expansion factor in the adiabatic process as a function of theta. Okay, so I have to calculate the volume expansion factor along 1 to 4, 4 to 1 process and the 2 to 3 process. Now since along the adiabatic segment there is no heat exchange, so dq is equal to 0. All right. So if I put dq equal to 0 in this equation, I get dE by d theta into d theta is equal to pdv, right? So then that is this thing which I get. From this I can write dv by v is equal to minus 1 by n kb theta dE by d theta into d theta, right? So if I integrate this equation now for the two adiabatic processes, so first I will integrate along for this particular adiabatic process from 2 to 3. That means the left hand side I integrate from volume V2 to V3, and the right hand side I would integrate from theta hot to theta cold. Okay, so I get this expression. Similarly, for the process going from 4 to 1, I integrate the left hand side from V4 to V1 and the right hand side from theta cold to theta hot. And again, I get this value. So you see that these are equal to each other. Therefore, the volume expansion factors for the both the adiabatic processes are equal to each other. So the ratio is the same. That is V1 by V4 is equal to V2 by V1, V2 by V3. All right. So if I now put this result that V1 by V4 is equal to V2 by V3 in this equation, then you will see that the numerator and the denominator cancels out. This part of the numerator and denominator cancel out because they're equal. And from that I get Q hot by Q cold is equal to theta hot by theta cold, right? And from this expression, you know that Q hot by Q hot is cold is equal to T hot by T cold. In this way, we can actually say that the two temperature scales are equivalent. So ultimately what we get is that theta hot by theta cold is equal to T hot by T cold, right? So theta and T are proportional to each other. So uh, this is clear now, this question. Okay. If you have any question, you can ask. Okay. So if there are no questions, I will move on to the next question. So the next question is about the equation of state. So you know that the equation of state, it constrains the form of the internal energy. For example, for an ideal gas, you've seen that because the equation of state is basically PV is equal to nRT, from that you can say that the internal energy is only a function of temperature. For some other equation of state, you can have the internal energy being a function of volume and temperature as well. So that is what we will see in this particular question. So what does this question say? That starting from the first law of thermodynamics, that is dE is equal to TdS minus PdV, show that the equation of state of an ideal gas PV equal to nKT implies that E can depend only on T and nothing else. Okay, so you have to basically show this for an ideal gas starting from the first law of thermodynamics. Right. So in general, we start off by saying that the internal energy depends on temperature and volume, and my entropy also depends on temperature and volume. And then we will show that the internal energy is independent of volume. So how do we do this? So dE equal to TdS minus PdV. You can actually break up ds into two parts. Because s is a function of t and v, ds can be written as del s del t at a given v into dt plus del s del v at a constant t into dv, right? So that's how if you break up ds, then you can get this particular form of the right hand side, right? So then if I take a derivative, partial derivative with respect to v of the internal energy at a constant temperature, then I get del E del V at a given t is equal to T into del S del V, right, at a given t. This term becomes equal to 0 because I'm taking it at a constant temperature, and minus P, right? Okay. Now what I do is that I use Maxwell's relation. So according to Maxwell's relation, del S del V at constant t is equal to del P del T at constant V. So this is a very well-known relation which you will find in most books on thermodynamics. So if this is equal to this, then I can substitute del S del V at constant t in this equation. And what I get is that del E del V at a given t is equal to t into del P del T at constant V minus P. Okay, now if I use my ideal gas equation that PV equal to NKT, and then I calculate del P del T from this particular equation, what you will find is that this term becomes equal to P. Okay, and so this thing becomes equal to 0. As a result, E only depends on P, sorry, and not on volume. In this way, starting from the first law of thermodynamics, you can show that the internal energy of an ideal gas depends only on temperature and nothing else. So, is this clear? Okay, clear, no? Okay, if you have any questions, just ask me. Okay, the second part of the question says that what is the most general equation of state which is consistent with an internal energy that depends on only on temperature? That means we have to find the most general equation of state that for which the internal energy is only a function of temperature and nothing else. Okay, so if E is equal to E of T, only a function of temperature, then if I take a partial derivative with respect to volume at a given temperature, then it will be equal to 0. All right. And this would in turn imply that T into del P del T at constant V is equal to P. Why? Because this is what we get by using the first law and Maxwell's relation. Right. Now, if this is my constraint on the pressure, then you see that if I substitute P equal to some function of V into T, that means if my pressure is linearly dependent on T at a given constant volume, and it can also be any random function of the volume, then only this equation is satisfied. So any equation of state having this particular form where the P is linearly proportional to T at a given volume, for this equation of state, the internal energy will only depend on temperature. Okay. So now for a van der Waals gas, you have to show that the specific heat at constant volume, that is Cv, is a function of temperature alone. So the van der Waals equation of state is given in this form. This you might have come across in your courses. So from this, I can write P in this particular form. All right. Now Cv can be written as del E del T at a constant volume. Okay. Now we have to show that Cv is a function of temperature alone. So in general, I can start off by saying that it's a function of temperature and volume. And then I have to show that its derivative with volume becomes equal to 0. That is, it is independent of volume. So I take a partial derivative of Cv with respect to V at a constant temperature. So this is equal to del to V divided by del V del T, right? So I can take del T outside, and then I get del T of del E del V at a constant temperature, right? And del E del V at a constant temperature turns out to be equal to this. Therefore, this is del T of T into del P del T at a constant volume minus P. Now, if I substitute this equation of P, that is, I take the derivative of P with respect to temperature at a constant V, I will see that this part becomes equal to 0. So del Cv by del T is equal to 0, right? And in this way, you can actually show that Cv is independent of V and a function of temperature alone. Okay, so this question is clear, right?
Yes, sir.
Okay, okay. Moving on to the next question. This is based on the Clausius-Clapeyron equation. Okay. So uh, Have you read about the Clausius-Clapeyron equation? Okay, so if you have not read about this thing, then I can give a small overview of it. So Clausius-Clapeyron equation basically describes of the line of coexistence of two phases. So suppose you have water and gas coexisting. So at a boiling point, water and gas as steam coexist together, right? And the boiling point of water, it depends upon the pressure, right? So at a sea level boiling point is something. If you go to the top of Mount Everest, it will be something different, right? Because the pressure is different over there. So if you try to plot the variation of the boiling point on a pressure versus temperature graph, you will see that with pressure, the boiling temperature of water changes. Okay. And this particular line, the slope of this pressure versus temperature graph for the phase transition, this is given by the Clausius-Clapeyron equation. So how do they derive this particular slope of this line? That is that we assume that at the coexistence, the chemical potentials of the gas and the liquid phase are the same. Okay. So chemical potential is a function of pressure and temperature. For the liquid and gas, it is the same at the phase of coexistence. So mu of liquid at a given PD is equal to mu of gas at PT. Okay. Now, if I perturb it slightly and then take a derivative of it, then I can actually get how this varies with different temperature and pressures. All right. So then I can get dp dt along the line of coexistence. And this right hand side, this can be written in terms of these two quantities, small v and small s, where small v is nothing but capital V by n. Capital V is the volume of the system, and n is the number of uh, particles, basically number of molecules. Okay, number of moles. And similarly, s small s can be written as capital S by capital N. So this is the specific volume and the specific entropy. So dp by dt is nothing by Sg minus Sl by Vg minus Vl, where Sg is the entropy of the gas and Sl is the entropy of the liquid. Vg is the volume of the gas and Vl is the volume of the liquid. So this is the Clausius-Clapeyron equation, and this tells me about the slope of the line of coexistence of two phases on a PT diagram, on a phase diagram. Okay. So now the question is that what happens? So we have to show that the work output of this engine. So what is this engine? So one can also get the Clausius-Clapeyron equation by considering a Carnot engine which uses 1 mole of water. Okay, so at the source, that is at the critical point, the latent heat converts water to steam. Okay, there is an absorption of heat which converts water to steam, and it is an isothermal process because the temperature does not change. It is always at the boiling point of water. Now, after that, as it goes from there is a volume increase. As the pressure decreases adiabatically to P minus dP, there is an increase in the volume. So this is an adiabatic process. And again, at the sink, the steam condenses back to water. So basically, the steam gives out this latent heat and gets condensed back to water. So this is the second isothermal process. And then there is the second adiabatic process, which takes the water from this particular state to its initial state, P comma T. Okay. So this can also be this phase transition between water and steam to water. It can also be defined with the help of a Carnot cycle. So you have to show that the work output of the Carnot engine has this particular form, and hence from this one has to obtain the Clausius-Clapeyron equation. So how do we do that? So here they have shown the Carnot engine on a pressure volume graph. Okay. So let me first explain what this graph means. So this blue colored shaded area which you see over here, this entire place is where the liquid and the gaseous phase they coexist together. So this is the region of coexistence. On this side you have the liquid phase, that is water. On this side you have water vapor, that is the gaseous phase. And in between, in this entire blue area, water and steam they coexist together. Okay. So suppose my system starts from 1. It is initially at this point. So first there is an isothermal expansion as the water converts to steam, And during this isothermal expansion, it absorbs latent heat. Okay, so Q hot is the latent heat which is absorbed during this process. It goes to 2. It becomes water vapor. Now there is a volume expansion of the water vapor by an adiabatic process and it comes to 3. During this volume expansion, the pressure decreases, volume slightly increases, there is no heat exchange. And the temperature of the water vapor also decreases slightly, but it's still in the coexisting phase. That means vapor and steam, they're coexisting together. After that, what happens is that the vapor condenses back to water via an isothermal process. That means it gives out some amount of heat in the form of latent heat. And after it goes to 4, its pressure again increases and it comes back to 1. Okay. So this is how the Carnot cycle proceeds over here. So what we have to find is that first we have to find the work output of the Carnot engine. Work output of the Carnot cycle is nothing but the area covered by this particular graph. Okay, so we can, for simplicity, you can see that this looks like a trapezium. Okay, now if I assume that these edges of the trapezium are very steep, I can approximate the trapezium to be a rectangle. So this makes my derivation easier. So if I consider this trapezium to be a rectangle, then the area of the rectangle is nothing but V into dB, right? Why? Because V is this width and dP is this height. All right. So that is why the work done is equal to V into dP. Now, because I had approximated the trapezium by a rectangle, there exist certain errors. And this is the extra area which I had left out. Okay. So how do I calculate this extra area? So this extra area is nothing but the area of this triangle over here and the area of this triangle over here. Okay. Height of this triangle is equal to dP and the base is equal to nothing but del V by del P into dP. Okay, so del V by del P tells me how the volume is increasing as a function of pressure multiplied by the increasing pressure. So this will give me the length of the base of this triangle, right? So this will tell me the extra area which I had left out in my calculation. So ultimately, this is the area which had been left out. And as you can see, since the pressure increase is very small, so dP is a very small quantity. So this is of the order of dP square. That is why the work done during this entire process is VdP plus some quantity, a very small quantity of the order of dP square. So we complete the first part of this derivation. Now from this, we have to obtain the Clausius-Clapeyron equation. So how do you proceed with that? Well, the efficiency of the Carnot engine can be written as the work done by the heat input. Okay, which is nothing but 1 minus Tc by Th, where Tc is the temperature of the cold isotherm and Th is the temperature of the warm isotherm. All right. So QH, that is the heat which is absorbed during the heating part, is nothing but the latent heat of water. W, as we saw earlier, was V into dP. Okay. Let us assume that the temperature of the hot isotherm is T, and because the process is happening just at the boiling point of water, so temperature of cold isotherm is T minus dT, where dT is a very small quantity. All right. So what we get is that if we substitute this particular equation, these values into this expression for the efficiency of the Carnot engine, then W being VdP, the left hand side is basically a VdP divided by L, and the right hand side is dt by T. All right. Or in other words, dP by T is equal to L by TV. So in this way, we derive the Clausius-Clapeyron equation along the line of coexistence of the water and steam. Okay. So then, if we assume that the latent heat is temperature independent and the volume change, oh, by the way, is there any question? Okay, are there any doubts or questions? If there are no doubts, then I will proceed further. Okay, I can then proceed further. So if I assume that the latent heat is approximately independent of temperature and the volume change is dominated by the volume of steam, that is the whatever change in volume is dominated by the volume change of the steam, and we treat the steam as an ideal gas, then we can integrate equation 1 to obtain equation 1 is this equation, Cauchy-Clapeyron equation, to obtain the equation expression for P of T. Okay, so if you assume steam to be an ideal gas, then V is equal to N kb by T. Okay, then I substitute the value of V in this equation. Then what I get is dP by dt is equal to Lp by N kb T square. If I integrate this, I get that P is equal to some constant into exponential of minus L by kb into boiling point temperature. Okay. Now, the interesting thing is that there are other physical systems which also look like Carnot engine. For example, cyclones or hurricanes, they are analogous but not the same. I mean, they are very different from a Carnot engine, but they're analogous, like they're similar to a Carnot engine. In what sense? Well, water evaporates at the surface of the surface of the ocean. It converts to steam. The steam then rises up in the atmosphere. It condenses back to form water at the cool altitudes and falls as rain. And again, the cool air goes down, again heats up and goes up. So in this way, the hurricane also works in a cycle, which is like the Carnot cycle. And what is given here is that the typical values of the ocean surface temperature and the high altitude temperatures are of the order of 80 degree Fahrenheit and minus 120 degree Fahrenheit respectively. So this is basically like the temperature of the isotherms, the upper isotherm and the lower isotherm. So this is the temperature of the upper isotherm where the heating occurs, and this is the temperature of the lower isotherm where the cooling occurs. Okay, and the total amount of water, total amount of water vapor which gets evaporated in order to maintain the speed of a typical hurricane is of the order of this 90 million tons of water vapor per hour. Okay, so that much water vapor is getting evaporated per hour in order to maintain the strength of the hurricane. So then given this quantities, can we estimate the maximum possible efficiency and the power output of such a hurricane? And the extra information that is given to me to calculate the power output is the latent heat of vaporization of water. Okay, so if we now treat the hurricane as a Carnot engine, then the maximum efficiency is given by 1 minus the hot temperature by the cold temperature. Okay, the hot temperature was what? Sorry, 1 minus the cold temperature by the hot temperature. Okay, so the cold temperature is this and the hot temperature is this. If we write it in terms of kelvins, we can calculate eta max, which turns out to be equal to 0.37. Now the output power of the hurricane is basically nothing but the efficiency multiplied by the input power. And the input power comes from the evaporation of the water vapor. Okay, so power output is nothing but the input power, which is dq by dt multiplied by the efficiency, th minus tc by th. Okay, so then what this becomes is that the heat which is being input to this thing is basically the latent heat of vaporization of water multiplied by the total amount of water that is being evaporated. Okay, so this is the mass of water being evaporated per unit time. I multiplied that by the latent heat, and this gives me the total amount of heat that is being input to the hurricane. If I multiply it by the efficiency, then I can calculate the power input into the hurricane. Okay, so is this question clear? Okay, so if this is clear, then I will move on to the next question. Now, as I was saying earlier, the boiling point of water at sea level can be different from that on top of a mountain, like Mount Everest. So because of gravity, you know that the atmospheric pressure can decrease with height. Now, by balancing the forces on a slab of air of a thickness dh, you can actually calculate what, and then integrating this the pressure differential, you can actually calculate what will be the pressure at a given height by knowing the pressure at some other height. Okay, so if P0 is the atmospheric pressure, I can calculate the uh, pressure at any height above sea level using this methodology. Okay, so first I take a slab of area A between heights h and h plus dh. Dh is a small quantity. Okay, then the total gravitational force due to the mass of particles in the slab is nothing but mg into total number of particles which are there in the slab. So such that each particle has a mass of n. The total number of particles which are there in the slab is basically the n into the volume of the slab divided by v. Okay, and this v can be written if I assume the air to be an ideal gas, then I can replace n by v by p by kBt. Okay, so this is the total force due to all mass of all particles in the slab. And we also know that force is pressure per unit, sorry, pressure is force per unit area. So force is basically pressure multiplied by area, right? Okay, so dF, so again, the force due to the pressure is equal to dP by d minus dP by dH into A into dH. So if I equate these two quantities, then I can calculate what will be the pressure at a given height h in terms of P0, where P is the pressure, P0 is the pressure at height h equal to 0. Okay. So using these results, I can actually calculate what my boiling temperature of water will be on the top of Mount Everest. Okay, which is at h equal to 9 kilometers. So if I use replace P0 by the pressure at sea level and h by the height of the sea level, then P Everest will be the pressure on top of Mount Everest. All right. And this can also be written in terms of the Clausius-Clapeyron equation. So I can use the result which I got over here, that is this particular value of pressure. And then from that, I can write it in terms of the boiling points at the two places. That is the boiling point of water at Everest divided and the boiling point of water at sea level. Okay. From this, I can calculate the boiling point of water at the top of Mount Everest by knowing the pressure over there. All right. So any questions or queries till now? Okay. So if there are no questions, I'll move on to the next question. So this question is about a hardcore gas. Okay. So you have a gas which obeys this equation of state P into V minus NB is equal to NKT. So if B is equal to 0, then this becomes my ideal gas. So in ideal gas, we assume the molecules to be point quantities, and that means we take the radius to be equal to 0. But if I consider my molecules to be hard spheres, that means if they have a finite radius, then I need to take into account the volume which needs to be subtracted because of their finite radius, right? So that is why instead of V, I write V minus NB, where NB is the correction which comes due to the finite volume of the molecules. So this is what is known as a hardcore gas or a hard sphere gas, where we consider the molecules to be have a finite size. Okay. So then P into V minus NB is equal to NKT. This is the equation of state for such a gas. This has a heat capacity Kcv which is independent of temperature. Now the Maxwell's relation is straightforward. It is the same as what we got before. That is del S del V at T comma N is equal to del P del T at V comma N. Now for this equation, it can be shown that the internal energy is a function of temperature and the number of molecules only. So how do we do that? We start from the first law of thermodynamics, that is dE is equal to TdS minus PdV. We again write S as a function of temperature and volume. Then ds can be written in this point in this manner: del s del t into dt at constant v comma n plus del s del v into dv at a constant temperature n minus pdv. Okay, then I use Maxwell's relation to substitute this thing. So del s, that is del s del v, is equal to del p del t. If I put del p del t over here, right? So then these two, uh, right? So if I put del p del t over here, then dE becomes equal to t into del s del t into dt plus this particular quantity. Okay. Now, from this equation of state, that is, we obtain that P is equal to nkt by V minus nb. If I take its derivative with respect to temperature, then this turns out to be equal to P by T. All right. So then this basically becomes P minus P, which is equal to 0, and dE becomes equal to T del S del T into dt. Therefore, this shows that E is independent of volume, because basically this has been taken at a constant volume. That is, if I take a derivative with respect to volume, it will be equal to 0. Therefore, the internal energy of a hard sphere gas is independent of volume, right? So next we are told to calculate the ratio of the specific heats at constant pressure and constant volume for this hardcore gas. So the heat capacity at constant pressure is nothing but del Q del T at a given P. Del Q can be written, this can be written in terms of the first law as del E del T at constant P plus P del V del T at constant P. But since on E is a function of temperature alone, del E del T at constant P is equal to del E del T at constant V, which is equal to Cv. So we substitute this by Cv, then Cp by Cv is equal to 1 plus P into del V by del T at constant P into 1 by Cv. All right. And del V by del T can be obtained from the equation of state, and this turns out to be equal to nkb by P. So then we get gamma is equal to 1 by nkb by Cv. And this is again independent of temperature because Cv is independent of temperature. Okay. Um, are there any questions? Any doubts or questions? If you can ask me directly if you want. Okay. So if there are no doubts or questions, I will move on to the next question. That is by writing an expression for the internal energy in terms of pressure or volume or otherwise, show that an adiabatic chain satisfies this equation, that is P into V minus NB to the power by gamma is a constant. So from the equation of state, we have dE is a function of T only. So and Cv is independent of temperature. That is why dE can be written as Cv dt. Okay. Now the equation of state is over here. Right? So T is equal to nothing but P into V minus NB by NKB. So if I substitute for temperature, then I get Cv into dE of T, which is this quantity, right? So this can be broken down in this particular form, PdV plus V minus NB into dP. All right. Now, if there is an adiabatic change, then dQ should be equal to 0. If dQ is equal to 0, dE is equal to minus PdV. So I substitute a minus PdV in place of dE. And then from that, we obtain dP by P is equal to gamma into this particular quantity, which is equal to 0. Now, if I integrate this equation to obtain P, I will see that log of P into V minus NB to the power gamma is a constant. As a result, P into V minus NB to the power gamma is also a constant for an adiabatic change. Okay. And so coming to the last question in this problem set from the point of view of thermodynamics. So suppose I have this irreversible process. Okay, so consider two substances. One is at a temperature of T1 0 and other is at a temperature of T2 0. So these are the initial temperatures of the two substances, and they come to equilibrium at a final temperature of Tf by exchanging heat among themselves. Then, by relating the direction of heat flow to the temperature differences, the entropy change can be written in this particular form. That is, entropy change of the total system delta S is equal to delta S1 plus delta S2, where delta S1 and delta S2 are the changes in the entropies of the individual systems. Delta S1 is nothing but a integration from T10 to Tf dq1 by T1 plus delta S2 is integration from T20 to Tf del q2 by T1. Okay, this will be del q2. Now, since system 1 is exchanging heat with system 2, then so if I consider dq1 to be equal to this q, if I consider dq to be equal to dq, then dq1 should be equal to minus of that, that is minus dq. So in that way, we see that delta is equal to integration t1 minus t2 by t1 into t2 into dq. So you have to show that this should be positive. So in other words, this is basically another way of expressing the second law of thermodynamics. So the second third law of thermodynamics states that heat cannot flow spontaneously from a cold body to a hot body. Like for example, in a refrigerator, you can't have things cooling down hot, like a hot bottle of water cannot cool down on its own. You have to apply some energy to cool it down in the form of electrical energy, right? That's what a refrigerator does. So that's what the second law states, that you cannot have heat flowing spontaneously from a cold body to a hot body, right? Another way of stating this is that if you have heat flowing from a cold body to a hot body, then the entropy of the system will decrease. So the second law states that the entropy of the system can never decrease. For an irreversible process, entropy is always increasing, that is always greater than zero. All right. So we have to show that the entropy is change in entropy in this particular process shown in this particular system is non-decreasing. Okay. So if I denote dq12 as the heat flowing from system 1 to system 2. Okay. So if dq12 is positive, that means heat will flow from system 1 to 2 only if one is at a higher temperature than 2. That means T1 needs to be greater than T2. So you see that this integrand itself is positive. This will lead to delta S becoming greater than 0. Similarly, if dq1 to 2 is negative, then I can write this is negative, for example. Then T2 should be greater than T1, and this quantity will also be negative. So again, you will see that the integrand again becomes positive. And in all cases, so delta S is always greater than or equal to 0. Now you consider a gas with adjustable volume V, diathermal walls embedded in a heat bath of constant temperature T at a fixed pressure P. Then the change on entropy of the heat bath is given by delta S of the heat bath is equal to delta Q of the bath by T, which is basic, since the gas is itself kept in the heat bath, so whatever heat the bath gives, it is absorbed by the gas, or the other way around. So this is equal to minus delta Q gas by T. And delta Q of gas can be written in terms of delta E of gas, that is the change in internal energy of the gas, plus P into delta V, that is change in volume of the gas. Okay. Now, by considering the change in entropy of the combined system, that is a gas plus volume, establish that the equilibrium of a gas at a fixed temperature and pressure is characterized by the minimum of the Gibbs free energy G, which is equal to E plus PV minus TS. Okay. So if this is my Gibbs free energy, then delta G can be written as delta E plus P delta V minus T delta S, because I consider T to be constant. So entropy is changing. All right. So the total change in entropy of the whole system, delta S is equal to delta S of the bath plus delta S of the gas. Okay. So delta S of the bath is given over here. If I add to this delta S of the gas, then the quantity which I get in my bracket is nothing but delta G of the gas. That is the change in the Gibbs free energy of the gas. Okay. Now, entropy is always up. Uh, so the equilibrium of the system is established at a point where the entropy is maximized and delta S is always greater than zero. This implies that delta G of gas is less than zero. So at the point where delta S is maximized, this will be positive and greatest, which means that delta G should be negative and least. So maximization of energy in this case implies the minimization of the Gibbs free and sorry, maximization of the entropy of the system implies the minimization of the Gibbs free energy of the gas. Okay, so this is how by minimizing the Gibbs free energy, one can also attain equilibrium. All right. So these were the questions which I had to discuss today. So, are there any doubts or queries which you have? Or is there anything which you like me to discuss in the next class or today?
Sir,
Okay.
assignment என்ன sir?
Assignment. So, assignment. So, the current assignment I can't discuss because that is graded. I can discuss last year's assignments. So, that I discussed already in the first half an hour. Okay. So, if you have any questions, you can ask me, or if you have any doubts regarding any topic.
No doubt, sir.
Okay, okay. So then we'll then say end the meeting today, and we will again meet in the next day, same time. Okay.
Okay, sir.
Okay.